We'll continue our discussion on compression of database. Remember that we were looking at the following problem. You observe n sort of entries, data points in a database, and each entry comes from this fixed set X. And you would like to store them so that you can answer a search query computationally efficiently and you store less. Store them so that we can. So there are two requirements: efficiently answer a search query. So search query will ask you if y belongs to is y in the set that you have stored. And second requirement is that your storage should be less. Use less memory. Okay, and what we saw was this sort of best of the two world algorithms, which requires storage roughly equals to n log x, order n log x, because it was 2 plus 2n, and search computational efficiency order 1 per query. So just one short search is needed per query. And we did this using random hash. That's what we saw last time. And in this class, what we would like to examine is if the algorithm that we found, is it optimal or not in some sense. So recall that the algorithm that we used so our algorithm was randomized and worked with some probability and worked with probability greater than equal to, let's say, 1 minus delta. So the delta we chose is 1 by 1000. And in fact, we had bounded the expected length, but you can use Markov inequality to also bound the worst case length of storage. So with some probability, your storage will not be more than something. Okay. So we get this n thing and efficiency 1. Question is, can you do better? Can you do better than storing this order n bits? So we will show that indeed it's impossible to do better than this. This algorithm is in some sense optimal, and towards that we will establish a lower bound. And this lower bound is actually quite nice. It's not your usual lower bound that we have been seeing till now, and it's a little bit complicated, but it will look very simple because the steps, you can verify them easily, but difficult to come up with. But the reason I'm covering this lower bound here is to illustrate the power of information theoretic techniques in showing lower bounds. If you try to show this lower bound directly, then it may be difficult. Okay, so let's show the lower bound. So recall that our algorithm works for the worst case input. What is the input to our algorithm? What you have stored and what you are querying. And we made no assumption about it. It works for the worst case input x1 to xn and query y. Okay. Therefore, and I'm just saying it without much proof, and these things are covered in randomized algorithm. Sort of what I'm writing is sometimes called Yao's min-max theorem, but you can convince yourself it's true. Therefore, it will also work for any distribution, any random input. For a distribution of our choice. Okay, so I'll describe that distribution of the random input. We will use a specific distribution to prove our lower bound. Okay. So what is the distribution of our choice? So suppose we fix a set x1 to xn of distinct elements from x. So we will generate our input from these elements. Let b1 to bn be independent and identically distributed Bernoulli half. So these are just random bits. Bernoulli half means random bit. Random variables where xi was stored when only if bi equals to 1. So we have this random bit. This is a random input b1 to bn which indicate whether xi was stored or not. So we have described a random random input. Random input is this described by this vector b1 to bn, which are all random bits, independent random bits, and bi equal to 1 indicates that xi was stored. We have to now define the random y. Now the random y is one of these input. Further, let y be given by xj, where j is uniformly distributed on 1 to n and j is independent of b1 to bn. Okay, that's the other part of the input. J is independent of b1 to bn. Okay, so you have these two random inputs now. So what your algorithm does is it sees this input now described by b1 to bn. This is your input, goes into your algorithm, the one you have designed. Since it works for every input, it will also work for this one, and then it keeps something in a memory, which is m. M is that memory, and let's say we have L bits of memory. So m is this. Okay, and then later there is a query made. Okay, this is your j, which describes the query. So this is a search query, and the search looks at m and j and gives out an output. And what is that final output? That final output is yes or no. So it's a single bit. I'll call it b hat. Okay. So b hat. So what do you want to check from b hat? We want to check b of j. We want to make sure that b hat, the final output, matches b of j, because j denotes the index you're looking at, and you can go and just check bit j. And if bj equal to 1, b hat must be 1. If bj equal to 0, b hat must be 0. So what we want, or what we have for any algorithm, we have the algorithm that works, probability that b hat of m comma j is equal to b of j is greater than 1 minus delta. That's what we have. And from this we want to figure out if we can derive a lower bound for L. Okay, that's the goal. Okay. So we do it, we do an information theoretic lower bound proof here. This L, remember, is more than h of m, because m takes values in 0, 1, L, the entropy of m. But entropy of m must exceed the entropy of mutual information, the mutual information between m and all the bits that you have stored, bn. Okay. So now this can be written as h of bn. So we are trying to figure out how much information will m have about this bits, minus, because we are asking some question about bn. So for m to have some information that we need about this bit, we would claim that m must be at least something. So the L must be at least something. L must be at least this mutual information. Okay, this is a simple bound. Okay, so the information m contains about bn must be a lower bound on L. But what is this information? Now we'll derive a lower bound for this. These bits are random and independent, so this is just n times binary entropy of a random bit, that's just n, minus this guy. Now this guy can be written as j equal to 1 to n h of bj given m into bj minus 1. If we drop this guy, the entropy will only increase, right? So you will subtract more, so it will, the overall term will decrease. So this guy is greater than n minus summation j equal to 1 to n. Now these are the kind of manipulations which it's difficult to figure out what's happening in combinatorics, and you can the way to come up with this is really think deeply and think about what that there is no loss in this, but verifying is very easy. Okay, so n into 1 minus 1 by n summation j equal to 1 to n h of bj comma n. Okay, now what can we do about this term here? This term here, remember, j was uniformly distributed from 1 to n. So this looks like the distribution of j, and this looks like the distribution on bj given j. This is exactly equal to. Note that j was independent of m. This query that was made is independent of what you stored in the memory. Memory only depended on the randomization of the algorithm, and this query comes from outside. Okay, so this is equal to bj given m comma j. That's exactly the definition of this. Here we have used, since j is independent of m comma bn. Okay, this is my notation for independence. Okay, all right. So this is some conditional entropy of a bit, so you can view it as n into 1 minus expected value over the two random variables m and j of probability that bj actually, how should we proceed from here? Yeah, so maybe a better way to proceed from here is now use Fano's inequality. So we have this bound now. Now Now let's look at this term that we have here. We still haven't used the fact that you can recover bj as a function of m and j. Okay, that b hat. That's the second part of the algorithm. It can use this function and recover it. So by Fano's inequality, h of bj given m comma j is less than equal to probability of error times log of cardinality of this alphabet, which is 2 minus 1. So the first term is just 0, plus the binary entropy of the probability of error. Okay, so that's the probability that b hat is not equal to b hat. Just to be sure, let's write b hat as a function of m comma j is not equal to bj. But we know that this is less than equal to delta. This probability of error we are assuming is less than equal to delta. So this is less than h delta. And that's the proof actually. So what have we shown? We have shown that if you put this bound here and see, this is the lower bound for L, this implies that L must exceed n times 1 minus h delta. Okay, that's the lower bound. Alright, so this concludes the discussion on compression of database, the part that I wanted to cover. We first showed an algorithm which enables efficient search, order 1 search, by storing just order n bits, n log x, but order n, and because log x is something we're not caring about in the upper bound. And then we show that no matter what a randomized algorithm does, it can never store less than n bits. Okay, even when you allow probability of error delta, it stores n times 1 minus h delta. Okay, so that's roughly the proof here. And yeah, so this lower bound is quite amazing. It's very simple, but otherwise, if you don't use information theoretic methods like Fano's inequality, chain rule here, then it will be very difficult to argue this thing. Now it's just a half a page proof, right? So we barely just touched this problem of compression on databases, and this is actually a very current problem. For example, we never put any distribution on this x1 to xn. We just work with the worst case. But you may want to put a model on these database entries, and like suppose they are independent. Suppose you can imagine if they are independent and coming from the same distribution, and then you would like to solve the same problem. What is the answer? What is the corresponding thing to entropy? Okay, that can be one question. The other question can be going from beyond this search query to other kind of queries like comparison queries or other operations over the database. Okay, and this kind of problems are an area of active research, and I think a topic called succinct databases relates to this topic. Many basic problems are open in this setting. Just like we have very clean answers for compression of entropic compression of a sequence, there are currently not very clean answers for things like entropic compression of database entries, so that you can enable efficient search and efficient queries like other queries, comparison queries, greater than equal to, less than equal to queries, those kind of things. Okay, but I guess I at least illustrated the power of information theoretic tools in analyzing these problems. So we saw random hash and we saw a lower bound based on Fano's inequality. Alright, so this concludes our discussion on compression, and from the next lecture onwards, we'll start with the next unit. This 11th unit was a short one. From the next unit onwards, we will discuss a very different topic. We will start discussing channel coding. So till now we were looking at compression, where a sequence is given and you would like to store it. One way to think of it is that you want to transmit data over a channel which has no noise. Whatever you send gets received exactly, but you want to use the channel the least number of times, and therefore it's like it's similar to sending over a noiseless channel. Now what we would look at is the case of noisy channels. When this channel that you're using, it flips every bit that you send over it, and this is called the channel coding problem. We'll start with it from the next lecture in unit 12. Okay, see you in the next lecture.